Hello everyone, today we're going to discuss about molecular geometries. It's a part of Chem 102, and we're going to also discuss about bonding theories later on in the next slides. Before discussing about the molecular geometries, I just want to brief that in chapter 8 we saw the loose structure, and basically a loose structure help us to understand the compositions of the molecules and associated with the covalent bonds. However, one thing that loose structure is missing is that loose structure do not show one of the most important aspects of molecule, which is their overall shapes and at the same time shape of the molecules. The shapes and size of molecule of a substance along with its strengths largely determine the property of the substance. In fact, effectiveness of a molecule is depending on the shape and the size of the molecule, as well as on the charge distributions within it. So we're going to pay big attention with the shape of the molecules. In order to understand the shape of the molecules, I first want to explain about something called electron domain. So, for example, if I have a central atom A, let's say I have a bond here, and the neighboring atoms B, and let's say if I do a double bond here, and I have another B here, the molecular formula for this compound can be like AB3. So one of the things that's very important for a molecular geometry of any molecule or an ion is to determine the electron domain. Okay, the electron domain is how many bonds are associated with the central atom. In this case, A is our central atom, and B are a neighboring atom or adjacent atoms. And if you have a double bond or a triple bond, all electrons shared between those two atoms are on the same side of central atom, so they're going to count as one electron domain. So it doesn't matter whether you have a double bond or a single bond, to how many bonds that the central atom is sharing. That's called electron domain. So in this particular example, we're going to observe the central atom, which is A, is our central atom. The central atom in this molecule A has 4 electron domains. Okay, 4 electron domains. So that means you have 3 bonds, out of which one is a double bond, and you have 1 lone pair electrons. The lone pair electron is actually this guy right here. So you'll have a 4 electron domain. Why we need to know about the electron domain is basically the number of electron domain is going to tell us the geometry of the molecule. Okay, 3, 4, 5, 6 will gives us or we can able to predict what the structure of the molecule will looks like. So basically the number of electron domains will give us what the geometry will look like. And in the meantime, I would like to introduce you something called VSEPR. It's very important. What VSEPR stands for? It's called valence shell electron pair repulsion. What it means is that in the valence shell electron pair repulsion, the names look a little bit cozy, but in reality it's not that much complicated. what it says that the base arrangement of a given number of electron domains is the one that minimizes the repulsions among them. So that gives you the base geometrical structure of that particular molecule. So the first thing that we need to know is the number of electron domains. Okay, the number of electron domains. This is a very significant point. And once we determine the number of electron domains, we have to figure out a way what will be the right arrangement for the electron domains that they can minimize the repulsion among them. Remember, electron domains have the same negative charges, so they don't attract each other, but they repel each other. Okay, so that repulsion has to be minimizing, and that will give you the best arrangement for that molecule. So depending on the number of electron domains, we would have different types of structure. We will have a linear structure. We would have a trigonal planar structure, and we would have a tetrahedral structure, and we will have a trigonal bipyramidal structure, and we will have an octahedral structure. So how do we know we have linear or trigonal planar? Like I say, the important part is the number of electron domains. Let's say if you have 2 electron domains, the base structure that's considered for 2 electron domains is going to be a linear structure. And the linear structure has a bond angle, a proposed bond angles about 180 degrees. A trigonal planar structure has 3 electron domains that the central atom is shared with 3 bonds. It can be a double bond, or it can be single bond. It can also be a lone pair of electrons. So the approximate proposed angle for a trigonal planar will be around 120 degrees. A tetrahedral structure is having 4 electron domains, and the common structure, the common angle for a tetrahedral structure is approximately 109.5 degrees. A trigonal bipyramidal has 5 electron domains, and octahedral has 6 electron domains. Again, out of that, we're going to, some of them would have, if you have a lone pair of electrons, you might have a little bit different geometry at the same time. That I'm going to explain how we can able to break them down. Especially for linear structure, you have only one option. You have a 180 degree. But for trigonal planar, you may have a common trigonal planar with no non-bonding pairs, and then you will have a bent structure at the same time. A bent structure. I may give you some examples related how trigonal planar can be divided in a common trigonal planar and a bent type of geometry. So, for example, let's say that you have an element boron trifluoride. Okay, if you have a boron trifluoride, here we don't see any non-bonding pairs, but the bonding domains, this is fluorine by the way, I'm sorry for writing. Basically, we also have a lone pair of electrons for each atoms, but that's not contributed for the electron domain geometries. The electron domain geometry are 3 with no lone pair, so this is going to be a good trigonal planar structure. A good trigonal planar structure, and it will have an angle of approximately 120 degrees. But you may have a situation, something, for example, a nitrogen dioxide. So if you do the loose structure for nitrogen dioxide, and then the VSEPR theory will tell you that there is a minimum repulsion among each atoms from the central atom, you will have a lone pair here. This time you will have again, it's a 3 electron domains. That's very important. The number of electron domains are important, but among the 3 electron domains, the 2 are bonding pairs, and 1 is non-bonding. So we're not expecting here to have a trigonal planar geometry with 120 degree. The angle is going to be a little bit bent. So because of that reason, it's under trigonal planar electron domain, but we call this a bent geometry. And obviously the angle between them is not 120 degree, it's going to be less than 120 degree. But still, this is under a trigonal planar geometry because it has 3 electron domains. So a tetrahedral structure, like I said earlier, a tetrahedral structure has 4 electron domains. Now, if you have a central atom is bonded and with no lone pair, let's say that if I have CH4, so the VSEPR theory tells me that the electron domain geometry for carbon, this is called a methane, by the way. Carbon you will have on the center, you will have hydrogen on this side, you will have another hydrogen on this side, you will have the hydrogen like out of the carbon, out of the screen, and there is another hydrogen maybe behind. So they are not like in the same plane, they are pulling towards each other, so pulling is minimizing. So this is basically, if you look at it, it gives you a tetrahedral structure with an approximate angle of 109.5 degree. However, depending on the lone pair, still there are a geometry structure considered as tetrahedral but not necessarily have an angle of 109.5 degrees. I can give you a very good example. If you talk about water, for example, if you do the loose structure for water, obviously the oxygen will be on the central part and you will have the hydrogen. So there is a lone pairs for the hydrogen side, for the oxygen side. So basically you have 2 lone pairs here and 2 bonding pairs. So we will have like 4 electron domains again here. So the geometry will be a little bit different. So the oxygens are pulling towards each other, so you may have a bond here, you may have another lone pair here, you may have hydrogen here, you may have hydrogen here. So this is also a tetrahedral structure. So maybe like lone pair of electrons, they occupy a bigger territory, so this area and this area would be for lone pairs. These are very tight at each other. So regardless, it has a 4 bonding, 4 electron domains, but the angle is pretty much is going to be less than 109.5, but still it's under tetrahedral, but it would have a name called a bent geometry. Bent geometry. So in this case also we need to know the difference between molecular geometry and electron domain geometry. A molecular geometry versus electron domain geometry. In most cases there is like some kind of confusion between molecular geometry and electron domain geometry. Electron domain geometry is focusing on the distributions of electrons in the central atom. A molecular geometry is focusing on how is the atoms are arranged in a molecule. Okay, sometimes molecular geometry and electron domain geometry are the same, sometimes they are different. So when someone asks you molecular geometry, don't worry about the electron domains or how the electrons are arranged. Look how the atoms are arranged. For electron domain geometry, you need to look how the electrons are arranged. Okay. In this case, for example, the electron domain geometry and the molecular geometry are the same. They are tetrahedral. But in the case of water, the electron domain geometry is bent, but the molecular geometry is tetrahedral, is 4. Okay, so I would like to make this point clear to you. So the other one is going to be a trigonal bipyramidal. So what is this geometry looks like? Basically, again, everything has started with the number of electron domains. So a trigonal bipyramidal needs to have 5 electron domains. Okay, they can be bonded or lone pair of electrons, but altogether, once you pick the central atom, and what is that the central atom is attached to the neighboring atom, how many bond pairs or lone pair electrons are connected to the central atom, that determines the geometry. So if you have an ideal trigonal bipyramidal, you will have 5 bonding pairs, and there is no any lone pair, maybe 0 lone pair. Okay, so that is a trigonal bipyramidal. Okay, but if you do the geometry, and if you see that you may ended up with 4 bonding pairs and 1 lone pair, still it's under trigonal bipyramidal geometry, but it's called a seesaw geometry. Seesaw geometry. Then we will have like a bonding pair of 3 bonding pairs and 2 lone pairs. Okay, so in this case again you'll have a 5 electron domain geometry, but this time it's called a T-shaped geometry. The molecular geometry is called a T-shaped geometry. There is also something which is similar to linear geometry, but again you may be come up with the same name of molecular geometry, but the important thing is you need to count the number of electron domains. Let's say that you have 4 bonding pairs and 1 lone pair. Okay, that's called 1 lone pair. That's called a linear shape. But don't get confused with the 180 degrees. It's not 180 degrees because you have 5 electron domains here. 5 electron domains here. So we will have I'm sorry, the 4 bonding pairs and 1 lone pairs. It's basically that if you have 2 bonding pairs and 3 lone pairs, okay, that's called a linear. 4 bonding pairs plus 1 lone pair is called a seesaw. 3 bonding pairs plus 2 lone pairs would be T-shaped, and if you have 2 bonding pairs plus 3 lone pairs is linear. Now if you add them up, every of these molecular geometry provide you 5 electron domain. That's very important, 5 electron domain. And the last one that we're going to see is going to be octahedral structure. And octahedral structure also have various types of geometry based on the number of lone pair and based on the number of bonding pair of the molecules that you have. So the last one we have is octahedral electron domain. what is it? Octahedral electron domain, if you have electron domain, the number of electron domains that are attached with central atom would have to be 6 altogether. 6. That includes the lone pair and the bonding pair. Let's say that if you have 6 bonding pair and 0 lone pairs, then you'd come up with the ideal octahedral structure. Okay, but in some situation you may come up with 5 bonding pair and 1 lone pair. You would have a molecular geometry called a square pyramidal. A square pyramidal. Okay, and you may end up with 4 bonding pair and 2 lone pair. Remember, everything added up into 6 altogether. You will have something called square planar. Square planar. So in summary, we discussed here about electron geometry of the molecules. Why we are interested with electron geometry? Because the geometry of the molecule is very important for the characteristic of that molecule. In fact, they said that the effectiveness of a substance is not depending by the concentration, but how the atoms are connected by the geometry of the molecule, especially when you are dealing with the biochemistry reactions, with drugs, with some of the pharmacy products. It's not about how much that you have, it's how they can easily be reacted with your body metabolism. That depends by the geometry of the molecule. So they play a very great role in terms of effectiveness. So based on that, this chapter is actually explained from linear geometry up to octahedral geometry. So basically the basic foundation is a loose structure. You start with a loose structure, but loose structure puts everything on the same plane. Doesn't tell you how the atoms are connected, or doesn't tell you how the angles are formed. So we have to come up with a VSEPR theory, which is a valence shell electron pair repulsion theory. And the idea of valence shell electron pair repulsion theory is determined by how many bonded and non-bonded atoms are connected to central atom. And the repulsion of this bonding and non-bonding have to be minimized so that you can get optimum geometry. So from linear we get to octahedral structure. So this is about the geometry of the molecule. The next one we're going to discuss about the polarity nature of the molecule, and we're going to discuss about the hybrid orbitals, which is the valence bond theory and the molecular bond theory. And I hope you like this video. Please share the video and leave a like, and also leave a comment in the comment section. Thank you very much. I'll see you on the next video.